So let's say this chemical reaction has a standard state delta G, this delta G naught, of negative 500 joules per mole. What does that mean? That means when we're at standard state conditions, and remember that's what this naught represents. When we're at standard state conditions, this reaction releases 500 joules per mole. And again, we know a key component of standard state conditions is having 1 molar concentration of all reactants and products. So therefore, if we're at standard state conditions where we have 1 molar of all reactants and products, we know this reaction will release 500 joules per mole. And that's what the standard state delta G tells us. But what else does this tell us? Well, this tells us when we're at standard state conditions, so therefore when we have 1 molar concentration of all reactants and products, this reaction releases energy. It releases 500 joules per mole. So therefore this reaction under these conditions wants to form products, because when it forms products and when it goes in this direction, it releases energy. It releases energy. So therefore this reaction under these conditions wants to go towards products and wants to create more products. So therefore we can also infer that this reaction must have a KQ, an equilibrium constant, larger than 1. Why? Because we know when we are at standard state conditions with 1 molar concentration of all reactants and products, this reaction wants to create more products. So therefore it wants to go in this direction because it releases energy, so that's favorable. So it wants to go in this direction, creating more products relative to reactants. So therefore if we create more products and having less reactants, we'll have a ratio that's greater than 1. We'll have more products relative to reactants, so we'll have a ratio greater than 1. And that's just important to realize. Whenever we have a standard state delta G, a negative standard state delta G, that means the reaction releases free energy going in this direction, so it wants to form more products. So therefore, it'll at equilibrium, it'll have more products relative to reactants, so its equilibrium constant will be greater than 1. However, let's say we had a different situation. Let's say this reaction had a positive 500 joules per mole standard state delta G. So let's say we had another reaction, another kind of reaction, but this reaction had a standard state delta G of positive 500 joules per mole. Then when we're at standard state conditions with 1 molar reactants and products, we know this reaction requires energy going in this direction. It requires 500 joules per mole to go in this direction. So therefore we know this reaction wants to go in the opposite direction. It's not favorable, it's positive 500 joules per mole under these conditions to go in this direction. So therefore it wants to go in this direction. Going in the opposite direction would therefore be favorable. So therefore if we have a positive delta G naught, then under these conditions of 1 molar conditions, the reaction wants to go in towards the reactants, creating more reactants relative to products. So therefore at equilibrium we'll have more reactants relative to products, we'll have more reactants relative to products, so therefore this ratio will be less than 1. It will be less than 1. So whenever we have a positive standard state delta G, we have a KQ that's less than 1. But the point is, this standard state delta G and this equilibrium constant are intimately related. They're intimately related and they essentially tell us the same information. And again, because we're at standard state conditions where we have 1 molar of all reactants and products, based on this sign, we know whether the reaction wants to go in which direction, so therefore we can determine if there's more reactants or products, so therefore we can determine what the equilibrium constant must look like. And again, so these two terms are intimately related. The standard state delta G is intimately related with this equilibrium constant to this reaction. To this equation. For example, if you have the equilibrium constant of a reaction, you plug it into this equation, and as long as you know the temperature and the ideal gas constant, you use this equation, you can determine what the standard state delta G is, and vice versa. So again, you can use this equation and see how they're related. So this is standard state delta G when we're at standard state conditions with 1 molar concentration of all reactants and products. However, what if we had the same reaction? So again, let's say we had the reaction that had a standard state delta G of negative 500 joules per mole. So let's say we had that exact same reaction, but what if we're not at standard state conditions? Maybe we have 2 molar of A, and 1 molar of B, and 2 molar of C, and 8 molar of D. Then we're not at standard state conditions, because we know when we're at standard state conditions, we have 1 molar concentration of all reactants and products. But what if we're not at standard state conditions? And most of the time, we won't be at standard state conditions. This is kind of idealized. When we're at perfect standard state conditions with 1 molar concentrations, then this is how much free energy is released. However, we usually don't have standard state conditions. This represents a more realistic situation when we're not at these perfect standard state conditions. So under these non-standard state conditions, how much free energy is released per mole? How can we determine the delta G, not the standard state delta G, but the delta G in these non-standard state conditions? How much free energy is released under these non-standard state conditions? Well, again, to determine this, we need this equation. So if we want to find under these non-standard state conditions how much free energy is released, that non-standard state delta G equals the standard state delta G of this reaction. So we can't just ignore the standard state delta G. We still need to know that. But we also need to know the ideal gas constant, the temperature, and also the reaction quotient. So therefore, the reaction quotient has an impact on the delta G. So this reaction quotient, these conditions, these concentrations, which again determine the reaction quotient, this has a big impact on how much free energy is released. Under certain concentrations with a certain reaction quotient, we'll release a certain amount of joules per mole. However, under a different reaction quotient with different conditions and different concentrations, we'll have a different reaction quotient, so therefore we'll have a different delta G and we'll release a different amount of free energy. So therefore we know this reaction quotient is really important. These reactions, these current concentrations, which again, you plug them in to find the reaction quotient. So this reaction quotient has a big impact on how much free energy is released. And something really important to realize is maybe at standard state conditions, when we have 1 molar concentration of all reactants and products, we release free energy. We release 500 joules per mole. However, we could have different concentrations that are non-standard state, so we could have different concentrations with a different reaction quotient that has a different delta G. Maybe this time we have a positive. Maybe we'd have positive 10 joules per mole or etc. So just because at standard state conditions we had a negative delta G, it doesn't mean under conditions we'll always have the negative delta G. Under conditions, maybe we have a positive delta G. And again, it just depends on the reaction quotient. So again, how much free energy would be released under these conditions? What would be the delta G under these conditions? Well, again, we use this equation. Again, first we need to find the reaction quotient, and we know how we do that. We take these current conditions, the current reaction quotient, we plug in these concentrations. We would plug them in. If we were to plug that in, we'd essentially get a reaction quotient of 8. So we'd have a reaction quotient of 8. And we would essentially just plug in all these terms, a reaction quotient of 8. Let's say the temperature is at 300 degrees Kelvin, the ideal gas constant. And then again, we can't ignore the standard state delta G. So the standard state delta G, which again was negative 500, and again, joules per mole, I should include that. So now if we were to solve this, we would get a delta G of positive 4.600 joules per mole. So now we know under these conditions, the delta G is positive 4,600 joules per mole. So notice the drastic difference. Under standard state conditions, when we had 1 molar, and the standard state delta G was negative 500 joules per mole. We released free energy when this reaction occurred. However, under these different concentrations, and therefore with a different reaction quotient, now we have a positive delta G. Now this reaction actually requires energy going in this direction. So now under these conditions, the reaction doesn't want to go in this direction. Again, with this reaction, it released free energy going in this direction. So it wanted to go in this direction. However, under these conditions with this reaction quotient, it actually wants to go in this direction. It wants to go in this direction, and therefore that's why going under this direction has a positive delta G. So again, the key point is this standard state delta G tells us how much free energy is released under standard state conditions. However, this non-standard state delta G without the notches, this normal delta G, this tells us how much free energy is released under any other non-standard state conditions. If you know these non-standard state conditions, these arbitrary conditions, you can find out how much free energy is released. And again, by finding the reaction quotient and using this equation, and again, so under these conditions, the reaction wants to go in this direction. So again, the concentrations and these conditions can impact whether the reaction wants to go in this direction and releases free energy going in this direction, or it can impact maybe if we have these conditions, under these situations, the reaction now wants to go in this direction.